All right, here we go for part two. Uh, it says find dy by dx in each case. And again, we're trying to mix up the notations, Leibniz notation. We could think of it like that. That's completely up to us. But since it's like this, that's what I'm going to do. This shape isn't a circle. This is called the folium of Descartes. Notice there's a typo there. It's not Descartes. It's Descartes and Descartes. Descartes. Descartes was mathematician and philosopher. He's maybe more famous for his quote, "I think, therefore I am." That was Descartes. And he was also the one that came up with this grid system, this XY grid system, called the Cartesian plane, right? The Cartesian plane is named after um, Descartes. And this is his folium, apparently. This is his folium, which is kind of this loop shape. Find dy by dx for each. In this case, all we have to do is take the derivative. So if we think of it in pieces, it's not that bad, right? Take the derivative of that. Well, that's just 3x squared. I don't have to write x prime or anything like that because our independent variable is x. Here, when I take the derivative, I think of it as a chain rule, right? This is a function that's chain composition of functions. So the 3 inside function gets written down, then I take the derivative of the inside part. That's dy by dx. And then still got to take the derivative of y with respect to x, even though I don't know what y is explicitly, nor would I even want to try to do that. Now, what I got on the right hand side, this is, I could think of this in two pieces. I could think of this as a product rule. This is a product rule, right? Where I've got two functions, one that's 3x and one that's this y, which we don't know explicitly, but we don't really care. So I'm going to take the derivative of the first thing, which is just 3, write down the second thing, which is y, plus, because this is a product rule, write down the first thing, derivative of the second thing. Well, the second thing is just the function y, right? So I could think of it as the exponent being 1, and then it gets written down there, and then 0, and then the derivative of the inside thing is dy by dx. Then the trick here now is to solve for dy by dx, because it appears in two places. Last one was easy. Well, how do we do this? Well, I'm going to put all the dy by dx's on one side, all the non-dy by dx's on the other side, and hope for the best. So 3y squared dy by dx. Again, the same thing as this is y prime if you'd rather that. Dy by dx. I just wrote that on this side. There's the equal sign. 3y, and then this goes on the other side, minus 3y squared. Notice everything's got a 3 in it. 3 is everywhere. I could just divide everything by 3, right? Simplify things. And then because remember, I know I'm done when I end up with dy by dx equals something, right? I don't have that yet. Actually, I got two of them still. But how could I think of this? I'm going to think of this as a common factor. This I'm going to factor out on the left-hand side. I'm going to write that out front of a bracket. What's left over, write down my equal sign. What's left over in this term after I take this out? Well, it's just y squared. What's left over after I take out this? Here is minus x. And then on the left-hand side, I'm going to write all this stuff down. Okay, handy. Now what? Well, if I want to get this alone, all I have to do is divide by this huge bracket. There's kind of a nice symmetry there. And if I wanted to find the slope at a particular point, I'd have to put in x equals whatever, then calculate what y is. But that's the expression. And notice, it makes sense. The derivative is defined in terms of y and x, while the relation itself is defined by both x and y. So to have this explicitly as just x's, who cares? This this is implicitly defined as well. All right, B part is more fun. Um, who knows what this looks like? I betcha Desmos might be able to handle something like this. That would be funsies to see if it did, but we don't care. We just need to take the derivative. So I'm going to spend one line of my derivative tidying this thing up so it's getting into derivative taking form. Here now I can see this is a power of a function, right? I want to take the derivative with respect to x, so this is an inside function. The half comes down, I subtract the half, but then I need to take the derivative of the inside thing as well, right? Notice this other y prime dy by dx, they mean the same thing in this case. So I'm going to write y prime. Half comes down, subtract. And notice I don't have to do x prime. Why not? Well, because my independent variable is x. I don't need to write down the derivative of x with respect to x. It's just 1. And on the left-hand, or the right-hand side, rather, I've got another one of these product rules. And this is a fun product rule, right? Because I got two pieces here. Both of them are powers, so this is going to be a pain. Derivative of the first, write down the second, plus write down the first, derivative of the second. Now the derivative of the second part is a chain rule. The 2 comes down in front of the y, subtract the exponent, but then I got to take the derivative of the inside thing. I got to be careful. My exponent ones look like y primes, and maybe that's why Leibniz notation is a little bit nicer, cleaner in this one. Okay, there's the derivative. Now I need to solve for y prime. I need to get the derivative by itself, so that I want y prime equals whatever this is to get an expression for the derivative. Well, what do? Y prime's on one side, other stuff on the other side. You know what I'm going to do? I'm going to multiply everything by 2 first, just to get rid of these stupid fractions. Can I do that? Tidy this up a little bit. That's going to be 2 times this is 4x squared y. Notice there's not some nice symmetry in these implicit differentiate. Well, it's because there's symmetry in this relation, in this equation here, so it makes sense to be some symmetry in the derivative as well. Again, we're solving for that. So all of these terms on one side, all the non-y prime terms on the other side. Write down this, subtract x to the exponent negative a half, factor out. Can I see that factor without having to go to a different color? Sure I can. That's going to come out front. Big bracket on the inside here. Now to solve for y, this bracket goes on the bottom, right? Just divide, and I get an expression. Oops. Bet you I'm making arithmetic errors all over the place. I need you to help me. You're supposed to speak up. These negative exponents, we might think about trying to tidy this up a little bit, but it ends up being a big hassle. So I'm not gonna. I'm just gonna leave it like that. That looks good enough. There's some for you to practice. And notice this is later on in the textbook. I don't know why they don't put this stuff in chapter 2, but it's later on in the textbook, and some for you to try. All right, both just taking some implicit derivatives and finding some equations of tangents, and it should be a good review. And that's all I have to say about that. That's all I have to say about Unit 2.